Hello everyone, and welcome to this session on number systems. This is Ram Charan, and today we will explore how numbers are represented in computer systems. Let's dive right in. Number systems are techniques used to represent numbers in computer architecture. They allow us to express numbers in different forms, which is essential for computers to process and store data. But why is this important? When data is fed into a computer, it's converted into a numeric format based on standards like ASCII. Each type of data is assigned a numerical value, enabling the computer to understand and work with it. Number systems depend on four key factors. 1. The face value of the digit. 2. The base of the number system. 3. The position of the digit in the number. 4. The significant bits in the number system. These factors determine how numbers are interpreted and processed in computers. Let's start with the decimal number system, which is the most familiar to us. It uses 10 digits, 0 to 9. The base value of this system is 10, meaning it has 10 unique digits to represent any number. For example, numbers like 12,345 or 6,789 are part of the decimal system. In the decimal system, each digit's value depends on its positional values. For instance, in the number 457.23, the digit 4 is in the hundreds place, so its value is 400. This is the most significant bit. The digit 5 is in the tens place, so its value is 50. The digit 7 is in the units place, so its value is 7. The decimal point separates the whole number part from the fractional part. The digits after the decimal point represent tens and hundreds. So 2 is 0.2 and 3 is 0.03. The digit 3 is the least significant bit. Next, we have the binary number system, which is fundamental to computing. It uses only 2 digits, 0 and 1. The base value here is 2, meaning it has 2 unique digits to represent data. For example, the binary number 101011 represents a specific value in the decimal system. In the binary system, each digit's position represents a power of 2. For instance, in the number 100.01, the leftmost one is in the first place, so its value is 4. This is the most significant bit. The middle 0 is in the 2 to the power 0's place, which is 1, and its overall value is 0. The rightmost one is in the 0.25's place, so its value is 0.25. This is the least significant bit. The decimal point separates the whole number part from the fractional part. Now, let's look at the octal number system. It uses 8 digits, 0 to 7, with a base value of 8. This system is often used in computing for its simplicity in representing binary data. For example, the octal number 541.67 represents a specific value in the decimal system. In the octal system, each digit's position represents a power of 8. For instance, in the number 541.67, the digit 5 is in the 64's place, 8 squared, so its value is 320, which is the product of 5 and 64. This is the most significant bit. The digit 4 is in the 8th place, 8 to the power of 1, so its value is 32. The digit 1 is in the 1's place, 8 to the power of 0, so its value is 1. The decimal point separates the whole number part from the fractional part. The digits after the decimal point represent fractions of powers of 8. The digit 6 is in the 0.125's place, 8 to the power of minus 1, so its value is 0.75. The digit 7 is in the 0.015625's place, 8 to the power of minus 2, so its value is 0.109375. The digit 7 is the least significant bit. Finally, we have the hexadecimal number system, which is widely used in programming and digital systems. It uses 16 symbols, 0 to 9 and A to F, where A represents 10, B represents 11, and so on up to F, which represents 15. The base value here is 16. For example, the hexadecimal number B46.38 represents a specific value in the decimal system. In the hexadecimal system, each digit's position represents a power of 16. For instance, in the number B46.38, the B is in the 256th place, 16 squared, so its value is 2816, which is the product of 11 and 256, where B represents 11. This is the most significant bit. The 4 is in the 16th place, 16 to the power of 1, so its value is 64. The 6 is in the 1st place, 16 to the power of 0, so its value is 6. The decimal point separates the whole number part from the fractional part. The digits after the decimal point represent fractions of powers of 16. The digit 3 is in the 0.0625's place, 16 to the power of -1, so its value is 0.1875. The digit 8 is in the 16 to the power of -2's place, so its value is 0.03125. The digit 8 is the least significant bit. Let's test your understanding with a quick problem. Identify the positional value of the underlying number in the following examples. 1. In the decimal number 457.23, what is the value of the digit 5? 2. In the binary number 100.01, what is the value of the rightmost one? 3. In the octal number 541.67, what is the value of the digit 6? 4. In the hexadecimal number B46.38, what is the value of the alphabet B? Take a moment to think about it. In the decimal number 457.23, the digit 5 is in the 10th place, so its positional value is 50. In the binary number 100.01, the rightmost one is in the 0.25's place, so its positional value is 0.25 in the decimal system. In the octal number 541.67, the digit 6 is in the 0.125's place, so its positional value is 0.125 in the decimal system. In the hexadecimal number B46.38, the alphabet B is in the 256th place, so its positional value is 256 in the decimal system. Thank you for joining me in this session on number systems. We've covered the decimal, binary, octal, and hexadecimal systems, and how they form the backbone of computing. I hope this has been informative and engaging. If you have any questions, feel free to comment down.